Dear students, myself Kiran MP. I am working as Assistant Professor in the Department of Computer Science and Engineering in Government Engineering College, Kushalnagar. I welcome all of you for this session on inverse functions and properties of relations. Let us have a look at the agenda of this session. At first, let me study about inverse functions. So till now, you are familiar with functions, right? So now we see what actually an inverse of a function. Later, we will see some properties of relations such as reflexive relations, symmetric relations, transitive relations, and antisymmetric relations. Now, coming to inverse functions. Suppose assume f is a function from the domain A to the codomain B. I repeat, assume f to be some function from domain A to codomain B, and let B1 be some subset of B. I mean B1 is some subset of codomain B. Then F inverse of B1 is nothing but set of all those elements X that belongs to domain A, such that f of X belongs to B1. I repeat, F inverse of B1 is nothing but set of all those elements of domain A such that f of X belongs to B1. The set F inverse of B1 is called the pre-image of B under F. I repeat, the set F inverse of B1 is called the pre-image of B under F. Okay, so I think you are familiar with inverse functions. You came to know what actually inverse functions. So let me repeat, f is a function from domain A to codomain B, and B1 is some set which is subset of codomain B. Then f inverse of B1 is nothing but set of all those elements, say X, that belongs to domain A, such that f of X should belongs to B1. The set F inverse of B1 is called the pre-image of B under F. Now, let us have a look at example 1. See here, I have given two sets. One is labeled A with 6 elements. 1, 2, 3, 4, 5, 6. And the other set labeled B with 5 elements. 6, 7, 8, 9, 10. And let f is a function from the set A to set B. Okay, I mean domain is A and codomain is B. And let the order pace of this function f be 1, 7, 2, 7, 3, 8, 4, 6, 5, 9, and 6, 9. Okay, so I repeat, I given two sets, A with 6 elements and B with 5 elements. Also, I given a function f from A to B. I mean domain is A, codomain is B. Okay, and in this function f, 1 is mapped to 7, 2 is mapped to 7, 3 is mapped to 8, 4 is mapped to 6, 5 is mapped to 9, 6 is mapped to 9. Now, let we have some subsets of codomain B, such as B1 and B2. Here, B1 contains two elements, 6, 8, which is subset of B. Also, B2 contains two elements, 7, 8, which is subset of B. So now, to compute F inverse of B1, okay, I repeat, to compute F inverse of B1, okay, you look in function F. You look in function F for which elements of domain A 6 and 8 appears as an image. I repeat, to compute F inverse of B1, look in function F which elements of domain A, which elements of codomain B, to compute F inverse of B1, look in function F for which elements, I repeat, for which elements of domain A the elements 6 and 8 appears as an image. So when I look at function F, I see that for element 3 of domain A, 8 appears as an image, and for element 4 of domain A, 6 appears as an image. Is it? So for the elements 3 and 4 of domain A, 8 and 6 appears as an image. So F inverse of B1 is 3, 4. So similarly, to compute F inverse of B2, look in function F. I repeat, to compute F inverse of B2, look in function F for which elements of domain A the elements 7 and 8 appears as an image. When I look at function F, I see the elements 1 and 2 of domain A as 7 as an image, and the element 3 of domain A as 8 as an image. So F inverse of B2 is 1, 2, 3. So all of you are familiar, got clear with example 1. Now let us have a look at example 2. Here I given function f from R to R, and the definition of function f is f of x equals 3x minus 5 when input x is greater than 0, and f of x is minus 3x plus 1 when input x is less than or equal to 0. I repeat, the definition of f of x is f of x equals 3x minus 5 when input x is greater than 0. Yes, f of x equals minus 3x plus 1 when x less than or equal to 0. Now let me say for some elements of domain R, okay, 0 might have appeared as an image. I repeat, for some elements of R, okay, I mean domain R, 0 might have been appeared as an image. Now the question is, I need to determine which which are those elements of domain R? Which are those elements of domain R for which 0 is an image? Okay, I mean to say I need to compute F inverse of 0. So see, we don't know whether for input value x greater than 0 or for input value x less than or equal to 0. I repeat, we don't know whether for an input value x greater than 0 or for an input value x less than or equal to 0, f of x results in 0. Okay, so let me consider both the cases. So first let me assume 3x minus 5 to be 0. When I assume 3x minus 5 to be 0, I will get x equals 5 by 3. Look on the slide. When I assume 3x minus 5 equals 0, I will get x equals 5 by 3. Okay, and this 5 by 3 of course greater than 0. I repeat, x equals 5 by 3 is greater than 0. So 5 by 3 is one of the pre-image. Okay, one of the pre-image. I means one of the element in domain R for which 0 is an image. Okay. Second case. Now let me assume minus 3x plus 1 equals to 0. In second case, I will assume minus 3x plus 1 equal to 0, and I am going to find x to be 1 by 3. And this 1 by 3 is not less than or equal to 0. Got it? X equals to 1 by 3 is not less than or equal to 0. So the second case of function f of x fails here because the second case is invoked for an input x less than or equal to 0. But here I found x to be 1 by 3, which is not less than or equal to 0. Clear? So x equals 1 by 3 can't be pre-image. X equals 1 by 3 cannot be pre-image of 0. So only the element 5 by 3 is a pre-image of 0. This is how we compute f inverse of 0. And this is about inverse functions. Now let me proceed to properties of relations. So we all know relations, right? So what actually relation on or what actual relation from A to B is nothing but any subset of A cross B. So we know a relation from A to B is any subset of A cross B. Also we have word binary relation, that is relation on A is nothing but any subset of A cross A. So we know binary relation or relation on A to be subset of A cross A. Okay, so there are some 4 properties, okay, relations, okay, such as we call reflexive, symmetric, transitive, antisymmetric. Now let us study when we are going to call, okay, a relation to be reflexive or symmetric or transitive or antisymmetric or all or any few among these 4. Okay, first let me have a discussion about reflexive relation. So listen here, I repeat, listen cautiously. A relation R on a set A a relation R on a set A is called reflexive if for all elements X that belongs to set A, X, X should belongs to R. I repeat, a relation R on a set A is called reflexive if for all elements X that belongs to set A, X, X should belongs to R. What it means? A subset of A cross A should contain X, X. I mean a subset of A cross A, okay, should contain an ordered pair X, X for all possible values of X taken from set A. Okay, so let us have a look at example. See here, I have given one set labeled A with 4 elements 1, 2, 3, 4. Also I have given a relation on this set A. So that is nothing but subset of A cross A. Okay, and suppose if this relation R, which is subset of A cross A, I should call as reflexive means it should contain this four possible ordered pairs that are 1, 1, 2, 2, 3, 3, 4, 4. Apart from this ordered pairs, it can have any other ordered pairs too. Got it? So in this case, any relation R, I repeat, in this case, any relation R on A is said to be reflexive if it contains these 4 ordered pairs 1, 1, 2, 2, 3, 3, 4, 4. Now, see, I listed one example, R1 relation R1, okay, and this R1 contains 3 ordered pairs 1, 1, 2, 2, 3, 3, and this R1 is a relation on A, okay. Now, I won't call it to be a reflexive relation. I mean, R1 is not a reflexive relation on A because there exists an element 4 in A. There exists an element 4 in A for which an ordered pair 4, 4 does not exist. An ordered pair 4, 4 does not exist in R1. Got it? Let me tell you why R1 is not a reflexive relation. Because there exists an element 4 in A for which an ordered pair 4, 4 does not belong to R1. Similarly, when you analyze less than or equal to relation, okay, when you analyze less than or equal to relation on A, it's always reflexive. Okay, because 1 less than or equal to 1, 2 less than or equal to 2, 3 less than or equal to 3, 4 less than or equal to 4. I mean to say, if the relation defined such as R2, okay, relation defined such as R2 on A is less than or equal. I repeat, if the relation defined on A is less than or equal, okay, then we have all 4 ordered pairs 1, 1 because 1 is less than or equal to 1, 2, 2 because 2 is less than or equal to 2, 3, 3 because 3 is less than or equal to 3, 4, 4 because 4 is less than or equal to 4. So we call relation R2 a reflexive on A. Got it? So just go through example 4. use find modulo and relation R. Modulo and relation R defined as x is related to y. Okay, in this case x is for all x and y that belongs to integers. Okay, for all x comma y that belongs to z, x will be related to y if x minus y is a multiple of n. Okay, x minus y is a multiple of n. You've seen, once you analyze, you will feel this modulo n relation is a reflexive. Now, let us have a look at the second property of a relation, which we call symmetric. See, a relation R on set A is called symmetric if x comma y belongs to R. It should imply y comma x should also belong to R for all x comma y that belongs to A. I repeat, a relation R on a set A is called symmetric if x comma y belongs to R. Okay, I mean if an ordered pair x comma y exists in relation R, then y comma x should also belong to R. It means an ordered pair y comma x should also belong to R for all x comma y that belongs to A. Got it? So what it says, in a relation R, if there is a pair x comma y, there should also be a pair y comma x. So let us have a look at example 5. Here we have given one set A with 3 elements, 1, 2, 3. I repeat, we are given a set A with 3 elements, 1, 2, 3. Also we are given some 5 relations here. Okay, 5 relations, R1, R2, R3, R4, R5. We need to determine among these 5 relations, is any relation which is reflexive, any relation which is symmetric, or any relation which are both reflexive and symmetric, or which are neither. Okay, so let me analyze R1. So in R1 there are no pairs 1 comma 1, 2 comma 2, 3 comma 3, so it's not reflexive. But 1 comma 2 exists, it implies 2 comma 1 also exists. When I see a pair 1 comma 2, I can also see a pair 2 comma 1. Similarly, I can see a pair 1 comma 3. I can also see a pair 3 comma 1. So it's symmetric but not reflexive. Now let us have a look at relation R2. Okay, in R2 we have 3 pairs of the form x comma x, that is 1 comma 1, 2 comma 2, 3 comma 3 for all the elements of A. So R2 is reflexive. In R2 we see a pair 2 comma 3, but we are not able to see a pair 3 comma 2. So it is not symmetric. So R2 is reflexive but not symmetric. Now when I look at R3, it has 3 pairs 1 comma 1, 2 comma 2, 3 comma 3. So for all elements of set A, there exists a pair of the form x comma x in R3, so it's reflexive. Also it is symmetric. Okay, because if a pair of the form x comma y exists, then only I should see whether the pair y comma x exists or not. Okay, clear? So I repeat, if a pair of the form x comma y exists, then only I should see whether the pair y comma x also exists to conclude symmetric. But there is no pair of the form x comma y, so there is no question of searching whether the pair y comma x2 exists. Clear? So R3 is reflexive as well as symmetric. So now when I look at R4, it has space 1 comma 1, 2 comma 2, 3 comma 3, hence it's reflexive. It has a pair 2 comma 3, also 3 comma 2, hence it is symmetric. When I look at relation R5, it has a pair 1 comma 1, but it does not have pairs 2 comma 2 and 3 comma 3. I repeat, in R5 we don't have pairs 2 comma 2, 3 comma 3. So it is not reflexive. Sorry, it has 3 comma 3. Sorry, in R5 we have pairs 1 comma 1, 3 comma 3, but not 2 comma 2. So it is not reflexive. Also in R5 we have 2 comma 3 but not 3 comma 2. So it is not symmetric. I repeat, in R5 we don't have pair 2 comma 2. So R5 is not reflexive. In R5 we have pair 2 comma 3 but we don't have pair 3 comma 2. So it is not symmetric. So this is about symmetric relation. Yeah. This is about. Let us have a look at transitive relation. A relation R on set A is called transitive if for all x comma y comma z that belongs to A, and if pairs x comma y and y comma z belongs to R, then a pair x comma z should also belong to R. I repeat, in a relation R, if there are two pairs of the form x comma y and y comma z, there should be a third pair of the form x comma z that belongs to R. Yeah. So to call a relation R to be transitive, if there are two pairs of the form x comma y and y comma z, there should also be a third pair of the form x comma z. Let us have a look at example 6. Here we are given a set A with 4 elements: 1, 2, 3, 4, and I have given two relations R1, R2. So let me check whether R1 is transitive. So in R1 we have pair 2 comma 3 and pair 3 comma 4. Also we have pair 2 comma 4. So it is transitive. I mean I have the pair 2 comma 3 and 3 comma 4. So I should have the pair 2 comma 4 in order to call it transitive. Now let me analyze whether the R2 is transitive. In R2 there is pair 1 comma 3 and pair 3 comma 2, but we don't have pair 1 comma 2, so it is not transitive. I repeat, in R2 we have pairs 1, 3 and 3, 2, but we don't have pair 1, 2. So R2 is not transitive. So just analyze example 7, okay? That is the relation R on Z by A related to B if A exactly divides B. Okay, you see that it's transitive. Got it? I repeat, analyze example 7. That is relation R on set Z, okay, in which A is related to B if A exactly divides B is transitive. Now let us look at the fourth property of relation, that is antisymmetric. A relation R on set A is called antisymmetric, okay, if for all A comma B that belongs to A, okay, and for all AB that belongs to A, if we have the pair, okay, or if we have A related to B and B related to A, then A should be equal to B. Got it? I repeat, a relation R on A is said to be antisymmetric if for all A comma B that belongs to A, okay, if for all A comma B that belongs to A, if A is related to B and B is related to A, then A should be equal to B. I mean to say, in relation there are two pairs of the form A comma B and B comma A, then to call it antisymmetric, A should be equal to B. I repeat, if in a relation there are two pairs of the form A comma B and B comma A, then to call that relation antisymmetric, A should be equal to B. Now let us have a look at example 8. Here A equals 1, 2, 3, set of 3 elements. So I have given two relations, one is R and the other one is R1. So let me analyze R. In R, see here, let me analyze R. So when I look at R, I am not able to find pairs such as 1, 1, 2, 2, 3, 3. So R is not reflexive. I am able to find 1, 2, 2, 1. So I am able to find 1, 2, 2, 1. There is a pair 2, 3 but no pair 3, 2. There is a pair 2, 3 but no 3, 2. So it is not symmetric. Then there is a pair 1, 2 and pair 2, 1 but no pair 1, 1. So it is not transitive. So now to call antisymmetric, if there are pairs of the form A comma B and B comma A, okay, A should be equal to B is the condition. Okay. Now in R, I am able to see the two pairs of the form, two pairs. One is 1, 2 and the other pair is 2, 1. But one is not equal to 2. So it is not antisymmetric. Got it? See, to call antisymmetric, if there are two pairs of the form A comma B and one more pair B comma A, then A should be equal to B is the condition. In R, I am able to find 1 comma 2 as one pair and 2 comma 1 as another pair, but 1 is not equal to 2, so it is not antisymmetric. So when I look at R1, okay, look at R1 now. It has space 1 comma 1, 2 comma 2, but no pair 3 comma 3, so it is not reflexive. And to check whether it is symmetric means if there is a pair of the form A comma B, then there should be a pair of the form B comma A. But here in R1 there is no pair of the form A comma B, so there is no question of searching for a pair of the form B comma A. I repeat, in R1 there is no pair of the form A comma B, so there is no question of searching the pair of the form B comma A. So it means R1 is symmetric. So for transitive, if there are two pairs of the form A comma B and B comma C, then there should be pair of the form A comma C. But there are no such two pairs of the form A comma B, B comma C. So there is no question of searching a pair of the form A comma C. So it is transitive. Now antisymmetric, what it states, if there are two pairs of the form A comma B and one more pair B comma A, then A should be logical, A should be equal to B. I repeat, to call antisymmetric, if in a relation there are two pairs of the form A comma B and one more pair of the form B comma A, then A should be equal to B. But in R1 there are no two pairs of the form A comma B and B comma A, so there is no question of comparing A and B. I repeat, in R1 there are no two pairs of the form A comma B and B comma A, so there is no question of comparing A and B. So R1 is antisymmetric. So these are about properties of relations. Okay, so let me wind up this session. Thank you for listening.